Last day we ended our discussion at an ensemble learning technique, that is random forest, right? And we have seen how random forest is actually utilizing different decision trees to classify our data. Even after some outlier present in the data set, it can easily generalize a model. So today we will start with a new machine learning algorithm, which is a very crucial. The name is, as you can see here, support vector machine. So what is the meaning of this support vector? It will be very clear to you once we will dive into the the understanding of the actual algorithm. But before that, I want to start in a different way. Like, assume that you have a data set. Okay. So, and you have to classify the data set. So, and assume that the data set has only two features, x1 and x2. Okay. So, you can easily put the data set as a point on a 2D plane, and since the feature is 2D, naturally you can easily draw a classification line on the 2D plane, right? Now question is that what will be the equation of that particular line, that we have to find out. That actually we have already done. But if I show you like this, like what you can see here, that for the same problem, the points are same. There are 6 cases. What is the difference? The difference is present in the classification boundary. Like in this case, it's something like this. It's a little less, angle, having more angle, and it's very almost vertical. So what is difference in these four? I mean 6 different cases. The difference is the equation of the straight line, right? And we all know the equation of the straight line mostly depend upon the actually fully depend upon the intercept and the angle, like, right, y equal to mx plus c, m and c. So somehow because of the difference of different m's and different c's, we can find different classification boundary or classification line. And you see in these 6 cases, you cannot say that a particular case is wrong. Like each and every straight line can classify the points with 100% accuracy, right? So everyone is correct. But if I ask you that which classifier is the best, how you will answer? So from this question, we will start understanding support vector machine. Okay. So in general, if I tell you that since this is a classification problem, we can easily try to go for a logistic regression, right? We have seen that logistic regression also do a classification. And what is that? Logistic regression means actually a logistic function over linear regression line. So if you apply the equation of the straight line to a logistic function, which is specifically sigmoid function, if you can recall, you will get a curve like sigmoid function curve, that already I hope you can understand. But now what this sigmoid function actually does, it actually, if you closely watch the feature and the property of the sigmoid function, you will see it actually calculates, the distance between the point and the corresponding decision boundary. Something like this particular distance, or maybe this distance, or maybe this distance, or maybe this one. And as less this distance is, the probability of getting classified of this point in this particular site will be very less, right? Because distance is very small. If distance is huge, for example this point, the distance between this point and this particular line is very high. Naturally, the output of the sigmoid function in that case will be towards 1, that we have seen, because as distance increases, the it will be towards 1, as distance decreases it will be towards 0, that we have seen. That means for huge distance between points and the line, I can say that point in a particular class with much higher probability, and for very less distance between the point and the line, we can say the point in a particular class with very low probability. So now question is that because of this particular line, maybe for this case or this case or this case, whatever, what are the probabilities of this particular points which is very closest, almost you can say, to this particular line segment? If you closely watch 6 different cases, you will see that for a particular point, for example this point exists over here as well, over here as well, so everywhere the same point exists. But if you see the distance between the point and the line, that varies based on the line segment, right? Here the distance is very small, here the distance is little large, here again very small, here it is large, and so on. So obviously I will try to keep the decision boundary in such a way which can, and for which, for every point we can decide in which side the point is with much higher probability. So we will always try to decide the side of the point with very high probability. If it is possible, then the classification will be the probability of the classification accuracy will be higher. And obviously as a designer, that should be our goal, right? So now if you compare these points with this classification boundary, you see we can draw imaginary line, something like this. And what this imaginary line is showing? It is showing that the distance between the closest point of the boundary in both sides. This is the closest point of the boundary and this is the closest point of the boundary. So this is an imaginary line, assume, and definitely it has to be parallel, remember. So for 6 cases we have this boundary. If you closely watch the difference between these boundaries, this difference itself signify, I hope you can understand, that how good the model is with respect to the distance between the closest point with the boundary. Because as close distance will be, the probability will be less, and as higher the distance will be, the probability will be high. Probability of classify that particular point in that side. And always our intention will be to find a particular line segment which can give higher probability, right? So from this 6 cases, I hope visually you can understand that this last one has a very huge boundary between these two red dotted line. So naturally, this particular model, the model by which this particular classification boundary has been found, can be the best classifier among all the 6 cases. All are correct, but this can be best. And here the importance of SVM come. SVM means support vector machine. So what basically SVM does, the SVM try to select that particular hyperplane that can classify the point as widely as possible, and that is what our intention in previous slide you have seen, right? By the way, we have a new word here, hyperplane. What exactly hyperplane is, we will understand very soon. But just for time being, don't think it hyperplane. We should select the line, a straight line you can consider, just for time being. Okay. So let's come to the point, what exactly support vector machine is. Support vector machine chooses the extreme points or vectors that help in creating the hyperplane, and these extreme cases are called support vectors. So the name support vector is nothing but though represents those particular point which is the closest to the classification boundary. For example, in previous line or what you have seen, this particular point, if you see in this side and this particular point in this side, is those two vectors which creates this imaginary dotted red line such a way that you see no other point will be presented somewhere after this dotted line, and no other point in this side also presented before this dotted line. So these two are vectors on support of which we are creating a pipe something like this, and that's why it is called support vector machine. I hope now this is clear. So now let's do one thing, let's try to closely understand about that particular decision boundary and the support vectors. It looks something like this. So we have these points already, you have seen the similar case we are talking about. We have this point in this side, and you have seen that these are the 2 points which is the support vector of this particular problem. And you see, if this particular point touches this particular, what actually I'm doing here, I have drawn an imaginary straight line which touches on this vector x, this particular dot, which is definitely a vector. Similarly, I have created another imaginary line here dotted which touches another point here which is again a vector. The distance between this imaginary line and actual classification boundary is d1, and distance between this line is d2. Remember, d1 is always equal to d2. I have written d1 d2 individually, but actually you can say d1 is equal to d2, and d1 plus d2, the whole thing, the distance between two dotted red straight line is actually called this margin. And support vector machine always selects that particular straight line which can for which we can have maximum margin in the diagram. So that is the intention of the support vector meshing, is to maximize this margin. So before we dive into more on this support vector meshing, let's try to visit some basic mathematical intuitions.